Welcome everyone to day 2 of Organometallics. There was a problem with the in-class recording of the original video. So we're going to go ahead and record a lecture, not in live time, but for those who are following asynchronously, so that you'll be able to continue with the class uninterrupted. Some parts of it will not recapture the in-class experience, so apologies for that in advance, but we'll try to go ahead and do the best we can here. So we'll pick up where we left off at the end of day 1, and that was wrapping up our discussion of main group organometallic chemistry, specifically the chemistry of organoaluminum compounds. So as you'll remember, the theme coming out of the end of day 1 was one of bridging and multinuclearity in this series of organolithiums, organomagnesiums, and organoaluminum. So we'll pick right up on that theme. Like the other 2 compound classes we covered, organoaluminum compounds are often polymeric or oligomeric in the solid and solution state. So the archetypal example here is trimethylaluminum, which perhaps you're all familiar with, often drawn with the molecular formula aluminum Me3, but in practice, this is a dialuminum hexamethyl species of the structure shown here. I've included the bond angles, and you'll see significant deviation from the typical tetrahedral geometry of an sp3 methyl group. And at first glance, you might be uncomfortable with this structure because you violate one of the first rules that you learn in organic chemistry, which is not to draw 5-coordinate so-called Texas carbon. But here it's allowed because the type of bonding that is at play here is a 3-center 2-electron bond, depicted with the MO representation shown here. And one way to think about this, it might be helpful to some in the audience here, is it's essentially the analogous to the bonding at play in a 1,2 carbocation rearrangement or a carbenium ion rearrangement. In this case, we would have this as a transition state structure. One interesting point to note that has historical importance is that organoaluminum reagents have greatly attenuated reactivity in ethereal solvents, and in the early history, this slowed the development of use of organoaluminums in organic synthesis, because the standard solvent that was used for benchmarking reactivity against organomagnesiums, against organolithiums, were indeed these ethereal solvents like THF and diethyl ether. Eventually, it was learned that shifting away from these solvents really turns on reactivity, and that's how they're often used in the present day. Just one more example to round out the discussion here is triphenyl aluminum isostructural and isoelectronic to the example that you just saw, with the exception that now this carbon bridging carbon atom, this mu2 organic substituent here is a phenyl group, formerly sp2 hybridized, although you see in the bond angles here that there's some deviation here and some rehybridization at play. In terms of reactivity, I'll go through this part quite quickly. You have a handout here included with the other files for class for today that summarizes the reactivity of organoaluminums. And one of the points I want to make, just getting this back to first principles, is remember that at the beginning of day one, we covered the electronegativity trends across these series of metals and metalloids that can form bonds with carbon. And we said one way to anticipate or rationalize reactivity is to think about the electronegativity difference between that element that's engaged in bonding and carbon itself. So in the case of organolithiums and organomagnesiums, these are more electropositive elements compared to organoaluminum compounds. And indeed, as a result, the bonding is more ionic in character, and they'll engage in polar additions to particularly polar functional groups. For example, carbonyl compounds, nitriles, and activated alkenes. In contrast, organoaluminum reagents, now with aluminum being a more electronegative atom, can engage in additions to relatively unpolarized pi systems, such as those found in alkenes and alkynes, in a process called carboalumination, which is widely used in organic synthesis. Carboalumination, the initial addition step, is syn stereospecific. Secondary processes can then arise that can change that syn stereoselectivity to be net anti, but in the initial addition event, it is syn stereo specific. And to just zero in on some of the mechanistic details, we saw that these organoaluminums typically are most stable. The resting state is the dimeric form. So they'll dissociate to the monomeric form, which is the reactive form, engage in alkene, and they'll do so in an asynchronous process, first forming a bond between carbon and aluminum, highlighted here in red, and then from that carbocationic intermediate, or that Zwitter ionic intermediate, now you'll have an alkyl group shift from aluminum to the carbocationic center to form the CC bond, highlighted here in red in this rightmost structure. So we can then zoom in on what we would anticipate the rate law for this process to be, given this mechanism. And given the fact that we're showing here that the rate determining step is the addition of the monomeric form of triethylaluminum to the alkene, then we'll have a rate law where we have the dimeric species here with half order dependence, the alkene with first order dependence. And determination of this rate law was indeed one of the factors that helped elucidate the mechanism of this carboillumination process. The kinetic reactivity here is highly dependent on the substitution pattern of the alkene involved. And the general trend is less substituted alkenes react more quickly than more substituted alkenes. The fastest being ethylene, the next fastest being a monosubstituted alkene, the third fastest in the series that we're considering is 1,1 disubstituted alkene, and the slowest being 1,2 disubstituted alkenes. An important application of carboillumination in industry takes advantage of the enhanced reactivity with ethylene. And this is a process called the Aufbau process, developed by Karl Ziegler at the MPI for Poland Forschung in Mülheim in Germany, where I worked for 1 year after undergrad. So the Aufbau process takes advantage of the repeated insertion of ethylene into now a growing oligomeric or polymeric alkyl chain tethered to aluminum. And so this repeated addition allows the chain to grow, and then treatment with O2 followed by alcoholysis leads to long chain primary alcohols, which, as we all appreciate, are widely used in commercial surfactants. Okay, so we'll wrap up the discussion today, or we'll wrap up the discussion of the day one notes by turning back to the last problem of the day from day one, which is number 4 here. And this problem of the day asks to consider a series of organometallic events where initially this aryl bromide is treated with N-butyllithium followed by bismuth trichloride to give a new species A, which is then treated with CP2 cobalt, roughly 2 equivalents. That gives us another new species B, and it says here that species B is a catalyst for oxygen atom transfer from N2O. And this specific example is from the lab of Pep Cornea. Okay, let's go back to the iPad and we'll do this one together. So if you're following along online, feel free to pause it if you want to work this solution yourself. Otherwise, we'll jump right in. The first step, treatment of this aryl bromide with N-butyllithium, will lead to lithium halogen exchange, directly building on what we covered in class. And the byproduct of this, we draw it in quotes here, would be butyl bromide. And with excess N-butyl, this could react further to give butene and lithium bromide. Then in the next step now, following lithium halogen exchange, we react with bismuth trichloride. And that will trigger a transmetallation. We will replace the carbon lithium bond with the carbon bismuth bond. And generate as a byproduct lithium chloride. bismuth here will be in the +3 oxidation state. There's transmetallations are redox neutral at the, or this type of transmetallation is redox neutral at the metals involved. So it's bismuth 3 going in, bismuth trichloride, and bismuth 3 coming out. This type of bonding motif with tridentate coordination is known as a pincer ligand. In this case, an NCN pincer, just denoting the sp2 hybridized nitrogen, carbon, and nitrogen all coordinated to the metal, or in this case, main group element. Now, the last step we have is treatment of this bismuth, this aryl bismuth 3 with a reagent that we haven't encountered yet in class, which is this CP2 cobalt. So we can quickly determine the oxidation state of cobalt. This is a charge neutral complex. Each CP is -1, so that means that cobalt will be +2. Cobalt +2 is not particularly stable. It would prefer to be in the +1 or +3 oxidation state. And that gives us a hint for how this CP2 cobalt will react, which is as a single electron reductant. And we have 2 equivalents of it, suggesting that there's going to be 2 one electron transfer, 2 single electron transfer events. And so now we will reduce bismuth 3 to bismuth 1, and then we'll generate 2 equivalents of the cobaltocene or cobaltocinium chloride as the byproduct, with this now bismuth 1 low valent NCN pincer as product B. So why all the fuss to make this in the first place? That's because it engages in this very interesting reactivity profile or reactivity mode for a main group element, which has not been well documented previously, where it can engage in O atom transfer from N2O, which is, you might know, as laughing gas, or this is also a very potent greenhouse gas. So organic chemists would love to be able to do more with this greenhouse gas, but it has been challenging. It's kinetically difficult to pluck off oxygen from N2O and then use it for useful chemistry. But this bismuth catalyst can indeed do that, forming a bismuth oxo, and we'll cover metal oxo species later in class, so I won't get into the structural details of this. And then in this case, transfer the O atom to HB pin. Not the most immediately useful transformation for a synthetic chemist, but the key point here is the underlying reactivity, which is quite novel and certainly a very creative use of low valent bismuth catalysis. Again, an example from Pep-Cornet's group. Okay, that will wrap up the day 1 notes. So we'll now just slide right into day 2. And that will mean I will open a new file here. And our day 2 notes start with a problem of the day. So let me go ahead and share that, and I'll read that to you. So problem of the day number 1 for the day 2 notes. Cobalt-3 coordination complexes, which are called Werner complexes, have played an important role in the history of the development of the fields of inorganic and organometallic chemistry. Provide the 3D structure, or I think the way I phrased this in class is provide multiple possible 3D structures of the coordination complex cobalt trichloride tetra ammonia. And so if you're following online, take a minute to sketch out what you think one or more reasonable structures for this molecular formula would look like. And you can pause it to do so. And I'll go ahead and shift back now to the iPad. And I'll just show you what we were able to come up with as a class. And there are the structures shown here. So there were proposals of 4-coordinate cobalt, which could be of a square planar geometry, could be of a tetrahedral geometry, and you could imagine some combination of chloride ligands and ammonia ligands occupying any of these 4 sites. There are a number of different possibilities here that you could arrive, and we just abbreviated them here. You could also draw 3-coordinate cobalt. And there, again, there are different ways to draw that. Interestingly, at the in the early 1900s, this series of complexes was attracted a lot of controversy, debate, and discussion. And one of the prevailing models that a subset of the chemistry community was advocating for is the connectivity shown here, which is sometimes referred to as the Chattanooga choo-choo train representation of cobalt trichloride. Obviously, it looks somewhat fanciful by today's standards, but at that time there was a prevailing belief that the valence, or the oxidation state of the metal, and the coordination number of the metal needed to be identical. And if you have that frame of reference, or that frame of thinking, then you need to draw something that looks quite exotic like this to make it all work. And then the 2 structures that were put forward that are closest, that most accurately reflect reality, are the ones shown here, where you have an octahedral coordination geometry. There can be 2 different stereoisomeric forms here. So you'll notice these are subtly different. They're non-superimposable. In one case, the 2 chloride atoms are trans to one another, and then another, in the left case, and in the right case, they are cis to one another. And in fact, this feature of having stereoisomerism was one of the properties that Alfred Werner used to, among other pieces of data that I won't go into in the interest of time, but one of the key pieces of data that he used to advance this concept that the coordination number in the oxidation state did not necessarily need to be the same, and that there could in fact be 2 different types of ligands, and that there can also be inner sphere versus outer sphere ligands associated with the metal. And so this is I think an interesting example that allows us to put ourselves in the shoes of chemists in the 1900s who don't necessarily have the same tools that we have at our disposal today, such as X-ray crystallography, that we can turn to for structural elucidation. You could imagine back in this time how vexing it would be to confidently solve a structure like this. Of course, you can get at that time relatively early, you could get accurately determine molecular formulas through a form of elemental analysis. But then what that would actually look like as a 3D representation was very much a black box. And so Alfred Werner was the first one to systematize this and really establish the field of coordination chemistry, for which he won the Nobel Prize in 1913. And so this series of complexes, cobalt 3 with different combinations of water, ammonia, and halide salts are often referred to as Werner complexes. So then the geometries that coordination complexes adopt typically follow Pythagorean geometrical patterns, and we borrow nomenclature from Pythagorean geometry. And so this 6-coordinate species shown, we call an octahedral complex because if you consider the faces of this structure, it possesses 8 faces and is thus octahedral. And then the Crabtree textbook, he notes that it's a bit unfortunate that the nomenclature is based on the number of faces, not on the number of vertices, which to us would be more intuitive. So if at any point you have an existential crisis thinking, oh, the complex is octahedral but only has 6 ligands, that's because an octahedron has 8 faces but 6 vertices. So some general representations that we'll use throughout the class and that you'll see when you read literature in this field. People will, when they're talking about a generic coordination complex or organometallic complex, they'll refer to using this representation of M and then Ln, the N here representing that it's an unspecified number of ligands, and the L specifying that the ligand identity is also unclear. So if you're reading a paper on palladium catalyzed cross-coupling, you might see this in the catalytic cycle, meaning that you have palladium 0 with an unknown coordination state around it. And so why we take time to cover coordination chemistry is because organometallic chemistry is a subset, really a subfield of coordination chemistry. And many of the key guiding principles of coordination chemistry we follow also in organometallic chemistry. So in coordination chemistry, you will encounter complexes of the type shown here, and associated water molecules we call aqua complexes, just a bit of nomenclature there. And then moving to more organometallic complexes that look like this. So here's an example of a molybdenum carbonyl complex. And one of the key points is that as you move to sort of traditional inorganic coordination complexes, or organometallic complexes, you go from more ionic bonding to more covalent bonding based on the ligands that are associated with them. So an important concept in coordination chemistry and organometallic chemistry is chelation. We can cover this later in the class, but I like to cover it at this point because chelation also played an important role in the history of Werner complexes. And so here's an example of a chelated structure here, meaning a ligand that's bound to a metal in through more than one site. And the Greek letter that we use to describe chelated structures is kappa. And kappa refers to the number of single ligating atoms of a polyatomic ligand bond associated with a metal. So if something is kappa 2, this is an example of a kappa 2 bound ligand, but where you have two distinct single ligating nitrogen atoms that are contained within the same molecule of ethylene diamine. Other examples of chelating ligands are shown here, some of which you may have already used in the course of your research. We talked about pincer ligands. This would be an N pincer. Specifically, this structure is called terpene. You perhaps have used BINAP, which possesses a chiral axis through this biaryl linkage, and is used in first developed by the lab of Noyori, winning him the Nobel Prize, widely used in asymmetric catalysis, a really beautiful structure. And then the chelating ligand, the polydentate ligand, so the other language we'll use here is denticity. And you'll see the root here, dent, the same as dentist, meaning that like the number of teeth that you're biting into the metal with. So we'll refer to monodentate, bidentate, tridentate as coordinating through 1, 2, and 3 atoms. EDTA is one of the most common chelating or polydentate ligands that you encounter in your daily life. It's used for all sorts of things, including as a food preservative. It's used in buffers. It's used as a water softener. It's used as a metal scavenger, and so on and so forth. You literally encounter EDTA every day of your life in some way, shape, or form. I think showing, which hopefully you'll agree, illustrates the generality and ubiquity of chelation as an important driver. So EDTA is unique because it can coordinate through all 4 of the carboxylates as well as the 2 amines in a hexadentate fashion, but also can coordinate through lower denticity modes as well. Okay, so we'll take now a few minutes to cover some historically important examples of complexes that helped propel the field of organometallic chemistry forward. And the first that we will take a look at is the complex shown here, Zeiss's salt. This was first discovered all the way back in the 1800s, if you can believe that, by William Zeiss, working in Copenhagen as a pharmacist. And every time I read this, I always think that life as a pharmacist in the 1800s must have been much more exciting than in the 2020s, because every time I go to CVS, I don't see anybody doing organometallic chemistry. But in any case, Zeiss ran this interesting experiment where he took potassium chloroplatinate and heated it up at reflux in ethanol and got a mysterious looking solid out of this. And it would be many, many years before the structure would be confidently elucidated, all the way into the 20th century by X-ray crystallography. But as it turned out, this was the first example of the bonding mode depicted here between an olefin and a metal sintering, where the filled pi bonding orbitals of the olefin coordinate through a dative interaction with an unfilled d orbital on the metal, and filled d orbitals on the metal donate into the pi star antibonding orbitals through a mode of bonding that we now refer to as the Dewar-Chack-Duncanson model. And we'll talk more about this in a future class. And I'll leave it to you to think the mechanism by which this is taking place. But the only carbogenic entity in solution is indeed the reaction solvent ethanol. So you know that will have to be the source of ethylene ultimately in this reaction. There's a really nice historical review from just a couple of years ago in Organometallics that not only documents this the history and the mystery surrounding isosalt, but also the debate that ultimately led to putting together this bonding depiction. So why this made such a big splash is because it was not known that olefins could coordinate to metals in this way, and that's why it remained the source of controversy for quite some time. We covered Grignard reagents already in the previous class, so we won't say much more about those. I just refer you to the notes from the previous class. And then moving forward, a really interesting example of the intersection between organometallic chemistry and medicinal chemistry. This is the case of salvarsan, a drug marketed by Hoest, and it also has a second name here, arsphenamine. And this was developed by the lab by Paul Ehrlich, who is a Nobel laureate not in chemistry, but in medicine in 1908. And if you follow at all the career of Paul Ehrlich, you'll know that one of the concepts that he's is famous for having advanced is the concept of the magic bullet. The idea that you could have a organic small molecule or biologic. Biologics didn't, the concept of biologics being used in this way was not by any means mainstream in the early 1900s. But you have some kind of molecule, some entity that can navigate its way like a heat-seeking missile through the body and directly target the afflicted protein to either shut off that protein's that enzyme's function or restore its function. That's the concept of the magic bullet. And his first, what he thought was his first magic bullet is the molecule shown here, which I think if we look at this today, we would immediately be suspicious that any organic arsenic molecule is going to be the magic bullet that he's seeking for. But this indeed was effective as the first modern antimicrobial agent used to treat syphilis, and was marketed for many years, used as the prevailing treatment for syphilis. And one of the interesting facts surrounding salvarsan is that actually the structure remained not fully elucidated for many decades. And as recently as 2005, there was a structural revision based on mass spec data showing that salvarsan is in fact exists as a poly metallic as an equilibrating mixture of polymetallic forms, specifically pentameric and trimeric form. And you can see how this structural feature may not be obvious from the molecular formula, but in any case, an interesting example of a drug that was used commercially for many years, whose structure was actually not fully annotated. Okay, we'll then turn attention to problem of the day number 2, and I will navigate to the worksheet so that I can read that to you if you're following along online. This is another question that asks you to be a time traveler and go back in time to 1951, where Paulson and Kelly performed the simple yet paradigm shifting experiment shown below, where CP magnesium bromide, cyclopentadienyl magnesium bromide, was reacted with iron dichloride with the hopes of triggering an oxidative coupling to make the fulvalene structure highlighted in gray. In fact, much to their surprise, a red solid whose structure was not immediately evident was isolated from this reaction mixture. So the question asks you to think of not just one plausible structure, but all plausible structures that you could imagine, and then to design experiments using techniques and technology available in the 1950s to disambiguate between these possibilities that you came up with. So if you're following online, pause the video and take a minute to jot down a few ideas. And then we'll go ahead and cut to the discussion that came out of the class. Okay, so I'll shift back over now to the iPad. And again, the challenge here that I posed was not to just come up with one structure, but many possible structures. So the class took that assignment seriously and came up with a number of interesting structures, some more exotic looking than others. Included among them are the sandwich structure shown here, and perhaps looking familiar. You could imagine an isomeric version of this sandwich structure, where you have what we would refer to as a eta-1 bound CP. So eta, we'll define this in a moment, but that refers to the number of atoms in a ligand capable of coordinating through contiguous atoms bonded to the metal center. So you could have a eta-1 coordination node. You could have an eta-1 coordination node, or an eta-5 coordination. And all of these are isomeric to one another. Now you could have structures as well that contain magnesium. You could have a product that's just CP2 magnesium. You could have a structure that looks kind of like the turbogrignards that we covered before that can be tetrahedral at iron and magnesium with CPs bridging. And then you could extend that reasoning and think about a oligomeric or polymeric structure. And all of these, based on information provided, are reasonable to consider. And so, in terms of experimental techniques, right away you could use elemental analysis or perhaps even a flame test to figure out what elements are and aren't present, and that would allow you to rule out anything that's magnesium containing. So that those are starred in green. You could rule out those structures. Now, I think more challenging, more subtle is distinguishing among the three possibilities shown in the top row, which again are all isomeric, so it all have the same formula weight and the same elemental composition. And so there you could potentially turn to IR and pay attention to the different inequivalent CC or CH, sorry, C double bond C or CH stretching frequencies, or NMR, which had already come online in the 1950s. The power is not what we're familiar with today, but would probably be sufficient for performing this experiment. In the NMR, you'd expect to see a single CH resonance in the structure, the sandwich structure shown in the orange box, whereas you'd expect to see multiple resonances, which I've tried to depict here for any ligand that's coordinated in an 801 fashion. And so this has an interesting history. The first paper that came out in 1951 actually showed the bracketed structure, proposed the bracketed structure shown here. And if you haven't had this experience yet, I'm sure you'll have it at some point in grad school, where sometimes you'll see something in the literature and you won't necessarily know quite what's wrong, but you'll know that it's wrong. And I think that was the case for several research groups here. When they saw this structure, they thought this does not look right. And one of the things that made people uneasy is that here you have in this bracketed structure essentially a dialkyl iron species, but it has profoundly high stability, which is unlike any type of alkyl iron known to date. And so that made people uneasy. And that prompted two different teams simultaneously, working independently, but working simultaneously to propose a structural revision to the structure we're familiar with, the sandwich structure shown in the orange box. And those two teams were one in Germany led by Fischer, and one in the States or at Harvard led by Jeff Wilkinson and R.B. Woodward. And some who are familiar with Woodward's career will know that one of his major contributions is structural elucidation through combination of IR and UV vis. And so it's interesting to see him collaborating with Wilkinson to apply those skills to this particular problem. And the structural elucidation of ferrocene and subsequent research on ferrocene as well as other metallocenes led to Fischer and Wilkinson winning the Nobel Prize in 1973. And not without controversy, you'll note that Woodward was not included among the Nobel laureates in this particular prize. And one point of nomenclature is that the term metallocene, the scene is meant to evoke the same sort of stabilization that one sees in arenes. So there was a recognition already that there was a property of aromaticity that underlied stability in these complexes. And this simultaneous discovery
for this simultaneous work sparked a decades-long rivalry between the groups of Wilkinson and Fisher that really came to define the field of organometallic chemistry. Okay, so with the remainder of the time that we have left, let's shift gears a little bit and now rather than focus on historical developments, we will focus on accounting, but not the type of accounting that helps you in for your taxes, which are due for everybody in the U.S. in just a couple days, but the type of accounting that helps you with thinking about organometallic properties and reactivity. And so to introduce this form of accounting, which we'll call electron counting, I'll introduce a few guiding principles. One is the 18 electron rule. And this rule, which I think in the Hartwig textbook, he doesn't like this term 18 electron rule. He describes it as an empirical trend, which is fine, but we'll just call it the 18 electron rule. It doesn't necessarily fall out of first principles, but it is indeed a trend that empirically we see, which is that in general, complexes with fewer than 18 electrons tend to be more reactive and tend to be unstable. And this is very much analogous to the octet rule that we see in the main group, or the S and P block elements. And we know in the main group, there are also exceptions to the octet rule, such as boron trifluoride. But we also know that those exceptions often imply some type of reactivity profile, and the same is true here with the 18 electron rule and molecules that don't follow it, that will break it. So the origin of the 18 electron rule is just like with the octet rule. It all comes down to atomic orbitals. So for any given principal quantum number, you have 5 d orbitals, and then at the next principal quantum number, you have 1 s orbital and 3 p orbitals, and together that will make, and then you have 2 electrons each, and together that will make 18 electrons. So let's consider one case study here, which is that of cobalt 0. So cobalt 0 has the electronic configuration of argon, and then 2 4s electrons, 7 3d electrons. And so this is considering filling up orbitals from lower to higher energy in considering atomic cobalt metal in the gas phase. But when you actually form a complex and you have a ligand field present, and we'll talk about what that means in a moment, then the order in which then the energies of the orbitals is perturbed, and the order in which you fill them up changes. So once a complex forms, now the 3d orbitals are lower in energy, and so they will get filled up first. And I realize, let's see, I have this text twice. And so we will consider cobalt 0, we will call it a D9 metal. And so this was a little confusing to me when I was first learning this. You'd learn that, cobalt has this electronic configuration, argon 4s2, 3d7, and people would call it a D9 metal. And I thought, no, isn't it a D7s2 metal? And again, this all stems from considering a gas phase versus actually considering a real complex with a real ligand field. So hopefully that's clear. If it's not, I think it will be clear as we go through more examples in the class. Okay, so for electron counting, we need to define different types of ligands that you will encounter in the course of your electron counting adventures. And there are 2 predominant flavors and then 1 more exotic flavor that we'll review very briefly. The first are so-called neutral donors, which we will call L-type ligands in this class. And the type of bonding they engage in is described as dative bonding, which is sometimes represented using this arrow representation shown here. In the old literature, this was very common for a period of time, and now it's sort of fallen out of favor, though some people still are very deliberate about using this. So some of the common neutral donors that you'll see, we talked about ammonia in the context of the Werner complexes. Phosphines are a common type of L-type ligand. We talked about water in the context of aqua complexes. CO is a common L-type ligand. And then you can have alkenes that are serving as neutral donors through, as I said, the filled pi bonding orbital, alkynes, arenes, etc. Another flavor is anionic ligands, so-called X-type donors. And these are said to engage in covalent bonding as opposed to dative bonding. This includes halides, alkoxides, carbogenic substituents like aryl groups, alkyl groups, as well as hydro groups. The key difference between these 2 is that if you consider their closed shell form, neutral donors are not charged and anionic donors are charged. So if you, by closed shell, I mean that the atom that's engaged and bonded to the metal has a complete octet in most cases, a complete suite of 8 electrons. Then you ask whether it's charged or not, or not charged. Now there's a more exotic flavor of bonding that metals can also engage in, which are called Z-type ligand, or bonding to Z-type ligands. And these are bonds where a filled d orbital on a metal coordinates to this ligand, which is typically a Lewis acid. So I've shown examples here of coordination to trialkyl aluminum, or coordination to tricoordinate boron. And we won't cover these in much detail, but I want you to know that they're out there. And then the key point from a electron counting perspective is that Z-type ligands don't bring any electrons to the party. They just engage in forming an associative interaction with this filled d orbital on the metal. So when it comes to electron counting, you won't count the Z-type ligands as donating electrons to the overall electron count. So the oxidation state is relatively, the oxidation state is relatively straightforward to determine. We will remove all the ligands and we will get them to their closed shell form, and then we will count the amount of anionic charge and then account for any overall charge the complex has. And then we will get to charge neutrality. And that will define what the oxidation state is. If that's not clear, it would be clear when we do examples. With electron counting, it's one of these things where you can discuss it as much as you want in the abstract. But really the way to get a handle on it is just do as many examples as you can. And hopefully we'll be able to do that together in class, and you'll have the opportunity to do that through homeworks as well. Another point that is very important is that this, when it comes to oxidation state, is that the oxidation state that we will determine based on this analysis is, at the end of the day, a formalism. It's accounting. It does not describe necessarily the true oxidation state, physical oxidation state of the metal. And in fact, often it will be way off from the physical oxidation state, because the Pauli electronegativity principle states that no atom in a complex will have an actual charge greater than +1 or -1. So we know, I'll just make one analogy. We know that in a quaternary ammonium salt, we draw formally a positive charge on nitrogen, but where positive charge actually resides, if you look at an electrostatic map, is on the flanking carbon atoms. And the same is true in organometallic complexes. Okay, so another important metric is the d-electron count. And this is relatively easy to determine. You first figure out the group number of the metal that's involved in this complex, and that you find just by what column in the periodic table it's in. Then from the previous step, you know the oxidation state, and you just subtract the oxidation state from the group number to get the d-electron count. And of course, you sometimes will need to adjust for the overall charge of the components. And the d-electron count, the physical meaning of the d-electron count is that's telling you the number of valence electrons in orbitals of predominantly metal character. So what that means, again, analogy to the main group, is if you have a tri-substituted amine, you will draw something like this, R prime, R double prime, and you won't always draw, but it's implied that they're there, 2 non-bonding electrons on nitrogen. And so the analogy here is that d-electron count is defining the number of, quote, non-bonding electrons that are sitting on the metal. A more precise way is to say that they're electrons that are in orbitals of predominantly metal character. And then you also have the overall electron count, which then this will typically this will often follow the 18 electron rule, but not always, as we just talked about, and that we get by adding the d-electron configuration, d-electron count, to the number of electrons from the ligands. So one point I want to make here is that there are 2 methods, 2 schools of thought for doing electron counting. One is the one method is the ionic method, and one method is a covalent method. And for the purposes and basically the only difference in this accounting scheme is whether you count the electrons in a given bond as residing in the metal or residing on the ligand. But whichever one you follow, you will get to the same. As long as you follow that method exclusively, you will get to the right answer. So we'll just learn one way in class, and that's the way that I'll do things. But if it's more intuitive to you to do it a different way, then you can read the book and learn the different way to do it. So let's now consider an actual example, and maybe this will hopefully become
clearer for you. And the example we'll consider is palladium dichloride bis acetonitrile. So the first step is that we're going to break all of the bonds between the metal. And I'll just put this in black so that you don't have so much pink on it. The metal and the ligands. We'll get back to 4 closed shell species. And we can also show the electrons that were involved in bonding here, those that we broke away from the metal center. And so very quickly we can see we have 2 negative charges. And that will mean that to have a charge neutral complex, you see overall this is not charged, that we'll need a +2 oxidation state on palladium. So then we can go through and figure out our metrics. So palladium 0 is a D10 metal, which means palladium 2 will be a D8 metal. We have now 8 electrons from the metal. We have 4 ligands, each of which is donating 2 electrons. And that will give us an overall electron count of 16. And immediately you'll say, wait, but we just learned about this 18 electron rule. Well, it turns out one exception to the 18 electron rule is D8 metals, which prefer to be square planar and are stable at 16 electrons. So another metric, another accounting number that is sometimes useful is called the coordination number. And the way that we will define this in class, for monodentate ligands, this is very intuitive. It's just the number of ligands. But for ligands that engage in more complex bonding, we need a more precise definition. And that more precise definition would be the number of electron pairs involved in metal ligand bonding. And we'll talk, I think these examples will illustrate the difference there. Now, I'm not a huge fan of coordination number because you can define it different ways and it will tell you different things. So for the purpose of this class, use this definition of number of electron pairs. But it's also not wrong to just define coordination number as the number of ligands, and you would get a different number. And so I want folks to know that this exists, but truth be told, it's not the most useful descriptor of organometallics. So isosalt, we have 4 ligands, no really tricky bonding going on here. So this is a straightforward case where the coordination number is 4. Now here is a more tricky one, ferrocene, our example from our problem of the day. How do we account for this? And more generally, how do we do electron counting for these more complex
polyhaptic or these hapticity greater than one type of ligands. So a CP ligand, I like to think of it as a combination of an alkene ligand, another alkene ligand, and then a lone pair. And the way that that's described then is you have two L-type ligands. We said that alkenes are dative ligands, and then essentially one alkyl ligand, one X-type ligand, or in other words, two L-X ligand. And that also tells us then that we have essentially three electron pairs per CP engaged in bonding. In other words, a coordination number, overall coordination number of 6 for ferrocene. So there's a handout that accompanies this class that has a bunch of different ligands and how you do electron counting for the more complicated cases like ferrocene, like CP ligands or AL ligands. And again, if anything, it seems unintuitive at the minute. The more examples you do, the more intuitive it will be. A general trend that is highlighted here is that coordination numbers of 4 to 6 are generally common for transition metals. And this stands somewhat in contrast to main group elements that have coordination numbers that can go as low as 2 to 6, 2 and as high as 6. Okay, so we've touched on this topic of hapticity, but now I'll formally define it as the number of contiguous atoms bonded to a metal, and this is denoted by the Greek letter eta. So if you hear eta 1, eta 2, eta 3, that's referring to hapticity. And it's different from kappa because kappa refers, as you remember from the part of the lecture on chelation, kappa refers to non-contiguous or discontiguous atoms. So hapticity is the number of contiguous atoms engaged in bonding. Let's consider the case of a benzyl ligand bonded to a metal. So it can exist in two forms, the eta 1 form, eta 3 form, and then the exchange between these forms are called a haptotropic shift. So in the eta 1 form, the way we do electron counting is it's a 2-electron donor, it's -1, it's X type. In the eta 3 form, let's think of it the same way that we used to think about the CP, where you have essentially an alkene type interaction and an alkyl type interaction. LX coordination mode. Now you have 4 electrons that the ligand is donating to the metal. Still, the overall charge is -1. But now the coordination number we would say is 2 because there are 2 electron pairs involved in bonding. And one of the key points that you'll notice, I'll just highlight here and then we'll wrap things up for today and pick it up, wrap up this lecture at the beginning of our day 3 class, is that these haptotropic shifts going from eta 3 to eta 1 actually decreases the coordination number, decreases the number of electrons being donated from 4 to 2, and that essentially opens a coordination site, or often will result in an open coordination site that a new reactant can coordinate to, and that's often a key step in organometallic catalysis. So we'll wrap things up there. Thanks everybody for tuning in. Sorry again about the recording problems with the initial classroom recording. We'll have this fixed for day 3 and beyond. And thanks again for tuning in.